Okay, well, we can make a start. So some people are still joining, but I would like to welcome you on behalf of EMMC and also our member Compular. I'm Gerhard Goldbeck. I'm the Executive Secretary of EMMC, and I'm here together with my colleague Ernst-Dieter Janotka, who to manage this webinar. This is a webinar in our series of webinars from our members. We're very pleased that Compular joined EMMC towards the end of last year. And today we're going to hear from Rasmus Andersen, who is the co-founder and CEO of Compular, who will surely tell you more about the company and what they're doing, but also very specifically on the topic of supercharging liquid formulation with multi-scale modeling and AI. The webinar is going to be recorded, and the recording is going to be made available to all of you and others who've registered and EMMC members. If you have any questions, please feel free to enter them in the chat as we go along with the webinar, and then they can be answered at the end by Rasmus. And also we have some obviously opportunities for direct conversation at the end as well. But in the meantime, during the webinar, please mute your microphones and close your cameras, and we'll focus on the talk. So now over to you, Rasmus. We're looking forward to your presentation.
Thank you very much, Gerhard. So I'm very happy to be here. We're a new member of EMMC. So we hope to be collaborating with a lot of those of you who come from the EMMC membership side. And very happy to have the opportunity to do this webinar. And as Gerhard already introduced, today I will be speaking about how you can supercharge and accelerate your liquid formulation R&D work using multi-scale modeling. And you'll also get the first ever oral presentation of our new AI model. So with that, I'm happy to dive in. So I might be preaching to the choir, given who is in the room, but you might wonder why liquid formulations is relevant, especially for a startup. So essentially, liquid formulations is key to many diverse application areas. And wherever they are, they have a lot of problems in common, which makes them tricky to handle in R&D work. And across most of these areas, the current state of the art is that most R&D work is still being done manually in labs with all the limitations of scalability and the inconveniences and costs that brings with it. So generally, you need to balance not just one or two, but a lot of different properties, and they all need to be good enough. Preferably, some of them needs to be really good. A lot of the time, a few of these properties are also very hard to measure well or in an economic or timely manner. And when we're talking about bringing new products to market, that time aspect is really crucial. It's also very hard to scale it up and down fast because it's limited by the instrumentation and the stuff that you have available. Then finally, if you're trying, for example, new ingredients, new additives, formulation, for example, very likely you will either need someone to synthesize it for you or you need to order it from a different company. In any case, this might easily take weeks to months of lead times to try something new. And as you might have imagined, we have a suggested solution for these problems. So our solution is a turnkey software where you can get access to multi-scale simulations of complex liquid formulations with a quite simple form, which is very simple in form to what you would have if you just wrote in your lab notebook before going out in the lab. Then all of that is automated so that we can just give you the finished results once the simulations are done, and you don't need to care about what goes in under the hood. The users of this don't need to be simulation experts. They can be the subject matter expert of the domain they're working in. And you can use this to predict material properties and all the way from molecular scale to device performance, and understand how it depends on composition, temperature, and operating conditions. It's also a good tool to get very deep into the insight of the inner workings of these formulations. And it's a good way to explain hitherto unexplained differences between different formulations, or different temperatures for that matter, or different process parameters. So one way that we are using this with our customers is that they can use it to eliminate around 90% of the candidates. For example, if you're looking to find a new additive for an electrolyte, as a favorite example of mine, then you might have a lot of candidates and you don't want to test all of them based on the lead times and lack of scalability. So what we can do is to do a pre-screening, and then you can go forward and spend the scarce lab resources on the 10% that actually are somewhat promising. And you can eliminate the lead times, and you can get down from months of time per iteration to down to hours. So you might ask, who are Compular? Who are we to propose this? And this is a company which was founded in Gothenburg in 2020 by myself and a few co-founders. It's a spin-out from Chalmers University of Technology, based on the research I did as a PhD student under Professor Patrik Johansson, who used to be at Chalmers Physics Department, who is now at Uppsala Ångström Laboratory. And Patrik is still heavily involved in the company as a board member. So the research behind it goes back to 2017 to 19 timeframe. And then we founded the company based on this IP in 2020. We had a slower start to kind of do the early work, but then in 2022, we raised seed money from venture capital firms. And since then, we've been doing pilots, we've been building the first version of our software, Compular Lab. And 2024, we got accepted into the EIC accelerator. And this has enabled us to further build the solution and expand from our initial segment of battery electrolytes to much more broader general liquid formulation R&D work. So if you hear me using a lot of battery examples, that is because that's what we have done most of. But right now we're in the process where we're really shifting to a broader application area, and we have some early experience in that. So our software is called Compular Lab, and it's a web application. And as I've already mentioned, it's meant to be really simple. You just input the composition and the temperature that you would like to study it. And then you hit run, and everything else gets done automated under the hood. And then you get the detailed results reports, which can give you the overall numeric properties, the viscosity, for example, but also detailed insights into the system. And you might also ask what goes on under the hood. And of course, the answer is a lot. This is a slide that aims to summarize it, but not in a way that I expect you to read everything or really follow in what's communicated there. So this is the overview, and I will go over each of the parts one by one. So hopefully they will make sense at the end. But in essence, this is a bottom-up approach where we don't rely on any experimental input from the customer. So because we're doing it basically from first principles and by stacking different scale modeling on top of each other, this means that we can work with anyone regardless of what data you have available right now. We use experimental data as touch points for validation, but not for training our models in the main simulation stack that we have. So yes, this will make more sense in a number of slides. I won't dive into the details, but if you're familiar with modeling, you might already get a hint from this slide. So yeah, I also mentioned in the title that we will talk about an AI solution that stands a little bit on the side. It's built on a very different tech stack, and I will also not steal the thunder. You will have to wait around until the end of the presentation to get a taste of that. But that is different, but also complementary and synergistic to our multi-scale simulation stack. So one of the main workhorses in our toolbox is molecular dynamics. And if you look at the picture here to the right, you might see that this AI picture was generated a while ago, before the image generation models knew that apples fall downward as opposed to upward. But yeah, molecular dynamics is basically Newtonian mechanics. There are versions based on quantum mechanics as well, but the Newtonian version is usually the better trade-off in terms of accuracy and computational cost, as long as you're careful about the parameterization. So essentially, you're solving Newton's equations for the acceleration, and based on that, you can propagate how atoms and molecules move over time. And for that, you need a model for the forces, because that's not something that you solve from quantum mechanics typically, but that you need to parameterize. And what you directly get from molecular dynamics is microscopic movement of atoms. Then you apply statistical mechanics to connect this to the macroscopic, or like the material level properties of the liquid. So for example, you can look at the movement over time of molecules, and then you use statistical mechanics to map that to a diffusivity on the macroscopic side. And the way that we are doing that, we have most of our core IP in the statistical mechanics step here, where we have a patented method based on the research that I did at Chalmers for how to identify what moves together and then do a lot of the analysis in terms of that. So I will go in and zoom in a little bit on that aspect. So we call this dynamic structure discovery. And the idea is that you look at the pairwise distances of atoms, and you look at how they change dynamically over time. So you might see something like the middle panel here, where something comes into close proximity, then it oscillates around a kind of equilibrium distance, and then it's maybe they go apart again. It stands to reason just intuitively that there should be some kind of algorithm for capturing that this is some kind of bond. We don't know if it's covalent. It might be like a van der Waals interaction or whatever, but for whatever reason, these two atoms stick together for a time as if there is a bond between them. And then we treat them as a bond and do time-dependent bond topology, which is maybe an overly fancy way of just saying that we look what sticks together, and then we analyze everything in terms of this. So this enables us to do a few different things. I think it's pretty obvious that we can use this to get a lot of insight, because then we can run statistics on these different dynamic species to see which species do we get, which dynamic species, but also how do they behave. Like each of them has a diffusivity, each of them has some kind of stability properties, and how often it changes structure, and so on. So this is also very good as an input when we go further to predict reactions, as you will see later. So this is in the middle of everything we do, and it's an ideal starting point for multi-scale modeling. So now this might look like, how to say, a malfunction, but it's actually movie time. So just for those of you who might not be very familiar with molecular dynamics, I'll show you what it is and how we do it. So this is what you get directly. This is just how atoms move. But then, of course, we also know what atoms belong in the same molecules. So that gives us another level of analysis, which we use more. And what Champion, this dynamic structure discovery engine, allows us to do is to look at the individual dynamic structures that form. So solvation shells, adsorbed species, that kind of thing. So what I've talked about so far is bulk molecular dynamics, which means that we look at a periodic box, it's repeating infinitely in all directions. The reason you do this is so that you don't have to consider boundary effects. And this is an ideal setting for doing the bulk speciation and characterization, but also to predict the overall liquid properties. So we can use this to predict things like viscosity, density, ionic and thermal conductivity, dielectric constant, heat capacity, etc., etc. And you might ask, is this actually useful in practical R&D? Do we actually match experimental values? And the answer of that is yes, by applying ourselves. So we've done a lot of benchmarking work and parameterization work in order to be able to have this good reproduction of experimental results. if you take a look at the overall molecular dynamics literature and you try to correlate it with experiments, it's very widely varying how accurate it is. I would say that we are probably in the state of the art there. And we also try to make it so that we don't use overly expensive simulations from a computational standpoint. So this is ionic conductivity and salt diffusivity, and at least for run-of-the-mill battery electrolytes, we're quite accurate there. But then sometimes you see some discrepancies if you're looking at other properties like transference number or thermodynamic factor. But if you look at them, the orange ones, which is the simulation, is actually a lot smoother and with smaller error bars than the corresponding experimental data here. And this is not because these experimentalists have been sloppy. I think this is quite generally considered gold standard for characterizing these kinds of electrolytes. It just so happens that some properties are quite hard to measure, whereas they're pretty trivial to extract from a simulation, given that you have a high quality simulation. So sometimes the question is, do experiments even match predictions? And if the MD predictions are correct and the experiment doesn't match it, then why don't you just do MD simulations instead? So just to give you a little bit more of an example, we recently did a collaboration with Solvionic, who are a company selling ionic liquids and ionic liquid electrolytes. So basically adding, for example, a lithium salt to an ionic liquid or a mixture of ionic liquids. So in the first row here, you see density, viscosity, and ionic conductivity as a function of salt concentration. And the diamonds are experimental data measured by Solvionic. The ovals are Compular's predicted properties. And as you see, we're following the trends pretty well there as well. And then the lower two lines are first neat ionic liquids and then ionic liquids with added salt in relatively equimolar concentration, or 2 to 3. So you see that for the neat ones, we're very close to the experimental values. For the ionic liquid salt mixture, we're not as quantitatively accurate, but we always get the right trends. And you see, especially for the viscosity, that we have somewhat flatter predictions. And this has to do with like the vast span of timescales involved as you, for example, move towards a lower temperature ionic liquid, and things really get sluggish. So everything I mentioned so far are things that the current version of Compular Lab handles. So if you just buy our software, these are things you will get. And I will now show you a few screenshots for what it looks like in the software. So the first part, what you will get when you create a simulation is that you will get a system that you can click into, and then you get to the results page, as we call it. And that has several sections. So the first section is the overall key results. So those are just liquid properties. And then if you take one step down and zoom in, you will get the molecular species view. So you can look at it in table format or in graph format. And what you get here is a list of the molecular species involved in the composition and a breakdown of each molecule's properties as extracted from the simulations. And then using the dynamic structure discovery, we can also go one level further down into dynamic species. So here you get a concentration ranked list of all the dynamic species. For example, the lithium ion solvation shells, for example. Then we move into something which you cannot yet buy this just in terms of software, but we are selling this now in terms of pilot projects, and that will apply for the rest of the multi-scale approaches. I will go through it. So the idea here is to not get rid of boundary effects, but to look at the interfaces that we're most often interested in, at least in electrochemical settings, which is charged metal surfaces or something similar to that. So what we do here is to use constant potential confined molecular dynamics. So we put a cathode and an anode, and we apply a voltage between them. If we want to, we can also have it and the 0 voltage between them. And then we can take a look at the electric double layer and do the same speciation analysis and species characterization there. So from this, we can get graphs like this one to the lower right, where we see, again, like how does the concentration of each of those dynamic species vary as a function of distance from an electrode. And the results here are shown in terms of what are the most common structures or dynamic species that we get on the anode, I think it is in this case. And then this is also the input that we do for electrochemical stability calculations. So if you look at the literature, there is quite widespread use of redox calculations in the Born-Haber cycle for those who are into DFT. But usually what people do is to either just handcraft the structures or they just do bare molecules. And then they compute the reduction and oxidation potentials. And what we have seen is that a lot of the results are cherry-picked in a way that the authors probably didn't mean to, but just by optimizing their workflows for a narrow chemical space, they get better results than if you optimize a workflow for a broader area. And what we found is that if you really want to be accurate in terms of this, you need to look at the solvation structures and especially the adsorbed species on the charged surface. So this is exactly what we do by using the dynamic structure discovery. We put it into quantum chemistry and then we can predict the reduction and oxidation potentials and also the detailed breakdown pathways. We get the activation energies and we get also how much free energy is evolved as a function of the reaction. So in the previous slide, I showed you just the adsorbed layer, but we can also zoom in and look at 3 different layers away from an electrode. We have the directly adsorbed layer, but we have also a second and third adsorbed layer. So this is again from a lithium-ion battery simulation. So we can see that for the first one, it's really always the lithium ion directly adsorbed. And then it always has a partial solvation shell. It doesn't have a full 4-fold solvation shell as it likes to have in the bulk. And then the second layer, there it's always 4-fold coordinated. In the first one, we never see an anion. In the second one, there is quite a lot of ion pairs. And we can even see some structure beyond that. Before we reach the bulk composition outside of that. And what we can also do is to look not just at the structure in this layer-wise fashion, but we can also build a dynamical model where we can look at the transition between different dynamic structures, but also how it transfers between the 3 different layers. So as I already mentioned, one use of this information is to put it in quantum chemistry calculations and to get the reaction mechanisms. And this we can do in multiple steps. We can identify the rate limiting step and then the input that we would need for a full kinetic reaction kinetic model of that. And once again, this is an application example. We were working with the Norwegian battery company Morrow Batteries, who have a high voltage chemistry that they are working on commercializing. And what they needed was something that could withstand the very high voltage of their chemistry. And in order to find this, they needed to try a lot of additives, where the additives needed to fulfill some electrochemical stability requirements, but also preferably some HF scavenging and other kind of functionality. So here we show you in an anonymized fashion what's the electrochemical stability window of the different additives that we tried. And the outcome of this project was that a few additives made it to coin cell testing, and then a further filtered set made it to full form factor pouch cell testing. And in the end, one of these additives actually improved on the reference formulations, where we were very happy about that outcome. So then once you put all of this together, you can take the transport properties, the understanding of how the electric double layer differs from the bulk and the transport properties and structure, both in bulk and EDL, and then also the chemical kinetics information. Based on all of this, you can put this into a continuum level model. So in batteries, this would be a cell model, Doyle-Fuller-Newman or pseudo two-dimensional model, as they're usually called. But there are similar kinds of models that will be relevant in different fields. The idea is to solve a bunch of partial differential equations on a grid. And by doing this, we could then look at, for example, charge-discharge cycles. We can look at aging over time, or rate limits, or reaction yields, or whatever it is that you're studying that we can capture with these equations based on those material properties. And once again, to reiterate, we're building it from the molecular scale to the device scale, only bottom up, not putting a bunch of stuff in at the middle. So this means that we're not reliant on customer or literature data in the same chemical space, which is a big strength. So once again, it's example time. So we did a project with ZSW. I'm not going to try to pronounce the full name, but this is a research institute in Baden-Württemberg in Germany. And here we coupled one of these electrochemical models, the pseudo 2D model, with a thermal model for the full form factor of a cylindrical cell, and then an electrical model based on a flattened version of the jelly roll. And here we try to kind of challenge the model a little bit. Like, what happens if we take a cell with a thick electrode configuration, so energy optimized rather than power optimized? If we put it at relatively low temperature and we then try to cycle it relatively fast, and then we see that we get very strong concentration gradients, as you would expect. The normal way of applying these models would be that you have just a single composition for the electrolyte in your model, and then you wouldn't capture this big concentration gradient and its downstream effects. I don't show it here, or you can see it in the lower left corner, what happened to the temperature distribution. So that's also pretty heterogeneous. So we have both concentration, i.e. composition, and also temperature being very heterogeneous. And most of the cell modelers don't capture this, but you can if you're using our model, because you don't need to measure a whole lot of different trials. And then if you're looking at the different properties, so you have these points 1, 2, 3, and 4. 1 at the anode, 4 at the cathode, and then you have the edges of the separator in between, where you have these different concentrations. And if we're looking at these 4 different points, that's what gives the 4 different curves in the lower half of this rightmost panel. And you see that you do get quite a lot of very different so salt electrolyte concentration, ionic conductivity, salt diffusion coefficient, transference number, and thermodynamic factor. They really diverge. Okay, sorry, I didn't mean to do that. And they also change over time, which is an effect of the heating that you do. And you can also find some work we did with Consol if you go to our webpage, where we look more into aging aspects, which we didn't capture in this work. So one thing worth noting as well is that even the current voltage curve looks quite different when we take this heterogeneity into account. So it's not just a matter of if you want to resolve the micro or the meso structure or dependence, but it also, like, even if you just treat the cell as an equivalent circuit, there actually is quite a bit of difference. Then, as I mentioned, we're also diving into new application areas. So if you're not into batteries, you shouldn't be discouraged from talking to us or working with us. We have a few small pilot projects ongoing in very diverse fields. So essentially what we did was that we just reached out in our extended networks. Whoever was quick to respond, we let them pitch what they want to do, and we try to see how well it fits into our simulation capabilities. So far, we've had a lot of success. There is a little bit of tweaking to do. We don't have anything here that we can yet publish, but if you keep track on our news feed on our webpage, you will probably get to see some more interesting results soon. So we have, for example, water cleaning of heavy metals. We have direct air carbon capture. molten salts for nuclear applications, and electrochemical means for isotope separation of heavy water that we have started looking into here. We're also quite curious about supercaps, liquid crystals, and ammonia production, among a lot of other things that we think would be a good fit, but which we haven't tried out yet. And you may also use the chat if you have any other suggestions based on what we do, what areas that you think would be really nice to explore with this, whether or not you would be interested in exploring it with us or using our tools. But then there is also the AI solution that I've been hinting at. So again, completely different tech stack. There are no simulations involved in this, but what it is an AI model that lets you predict liquid properties on around a second time scale rather than hours, which is necessary for the full multi-scale simulation workflow. And then another strength of this, so what it does, what the current version does is to predict ionic conductivity of an electrolyte composition as a function of the salt concentration and the temperature. And what it also does, so it gives you predictions, which are the curves here, for the conductivity as a function of concentration, but then it also shows you experimental data points. So all of these little crosses here can come from different papers, and you can hover over them. I'll see if I can manage a live demo after this. And then you can also draw this slider to titrate how many or how distantly related experimental data points you include. And underneath this, you get a reference list of the papers where the data is from. And you may click into any of those to get to the paper. Once again, the input is a very simple form, similar to a lab notebook. And you can just update it, then you hit run again, and then you get a new prediction. So one thing which we haven't built yet, but this is a matter of software engineering rather than scientific development, and that is that you can upload your own data here. So if you have unpublished data in your area that you're doing research or R&D in, you can just upload that data, and this will make the model better within roughly 5 minutes, because the part of the model that we retrain is so small that we can deploy it very quickly. And thus, over time, the model will get better for all the users. Then if you're a commercial R&D lab and you're not so keen on uploading your formulations, of course, there's a different tier for that. So you can get that privacy as well. But I think as far as researchers is concerned, it does make a lot of sense to have everyone help each other out. And then you can choose whether you want to, do you want attribution or do you not want attribution? If you rather remain anonymous, that's also fine. So the first product based on this model is called Formulation Explorer, and it is now available as an open beta, pretty limited. Not all of those features I'm describing here are live already, but you can sign up and then you will see when we ship these extensions. So yeah, future versions will add error estimation and out of distribution flagging. So if you go really wild and crazy to a part of chemical space, which the model definitely hasn't seen, then we will flag that and say, take this with a huge grain of salt. Of course, you can also see this if there are no data points that plop up. And this is a freemium model. So this is free for everyone for basic use. You will get a limited number of predictions per day unless you pay for it. Eventually, you will be able to earn more credits by inviting your friends and colleagues or by uploading your own data. And there will be different pricing levels depending on your needs. And eventually, we will extend this beyond just ionic conductivity of electrolytes to other kinds of properties. So this might be viscosity, density, solubility limits, electrochemical stability window. Yeah, whatever you could think of that would make sense as a liquid property, essentially. So one thing that we're quite interested in getting from the community today, whether you're in academic research or in industry, is what would you like to see? So I would be very happy if you felt like sharing that in the chat, and feel free then to write where do you work, like is it academic or industrial, and what property would you really love to see us being able to predict on a sub-second time. for liquid formulations. But then once we're done with all the features of the Formulation Explorer, we will also launch something called Formulation Optimizer. So it's the same model that does a lot of the heavy lifting here, but instead of just predicting liquid properties and have the user specify the formulation, we can have the user specify what they are looking for, and then have an optimizer using the model give a set of diverse candidate solutions who are all local optima for the different properties. And then we will respect the fact that that formulation work is always a matter of multi-objective simulation, multi-objective optimization. So you will be able to set a number of different properties that you would like to optimize and some relative importance of them. And then it will search in a diverse space for a short list of candidates which makes sense to iterate on. Then you can iterate on them using the Formulation Optimizer again, ask it to generate variations on things, ask it to generate more diverse areas, or just to locally optimize them further. And then you can, of course, at some point bring it to the lab, and then you do a lab iteration. You can upload the data that you get from that. That will improve the model. Then you can run another optimization run after that. And the objectives here is not only the physicochemical properties that the model predicts, but it can also be market data or environmental toxicity data and so on. Wherever we can find this data and bring it into the model, it can be part of the multi-objective optimization. And yes, before I move to my final slide, I would like to try a live demo of this. Let's see if I can manage to share something else. We're using Google Meet internally, so we'll see how nifty I am at sharing in Teams. It looks to me like you can see my screen now. So please, someone tell me if you can't. I will assume that you can.
Oh,
so
yes, very good.
Yeah. Okay, good. So this is what it looks like. Here is the form. I filled in here that the salt should be lithium hexafluorophosphate, and it should be varying from 0 to 3 molar. Then the solvents will be ethylene carbonate, EC, and ethyl methyl carbonate, EMC. That's 3 to 7 by mole part. I mean, I could also change, so we could do by volume, for example. And then I'll select the temperature interval. Right now it's set to 0 to 50 degrees. I guess that's fine. And I'll run predict again, and then it will make a new prediction. And here you see that we got new curves. The experimental data threshold is set pretty low. We still got, interestingly, some experimental data. So I think these are probably very close to the values of the simulation, but it's a bit too few, I think. So let's drag this up. And here you see that we get a lot more data, and you will just get a sense of how well they overall agree with the model's predictions. And then again, like the papers are all here. See what happens if I pick the one here. It looks to me like you, okay, are you a robot? This was not what I was looking for. Let's try another one. Oh, okay. So all the Elsevier journals seem to ask if I'm a robot. Let's see if I can prove I'm not. So anyway, the idea is that you will get directly to the paper. So this is also a pretty efficient way, actually, of doing literature discovery when it comes to these properties. So that was it for the live demo. I will, or perhaps I won't stop sharing. I will see if you will come with me. Do you once again see the slideshow? Looks like
Yeah.
it to me. Good. Yeah, so I hope this was interesting. I've tried to leave some room for questions, but before I'll open the floor for that, there are some action points depending on who you are and what you're interested in. So if you're in, especially if you're an industrial R&D lab and you think that you could use the Compular Lab multi-scale modeling approach, do contact us, and we'll see if we think it makes sense. So again, the software version is not yet feature complete, but parts of it is, and we are selling all of it on a pilot project basis, which means that we will be a little bit limited in bandwidth. So if you're interested in this, it's better to reach out to us sooner rather than later. And also, if you're involved in industrial R&D, perhaps you're a head of R&D or something like that, or a branch of the R&D, and you think that you should definitely get on the bandwagon of digitalizing more of your processes, but you're not sure how, we can also advise you on that based on having quite a lot of experience on what works and what doesn't work, both when we ourselves have tried to deliver simulation services to customers who have sometimes been happier than other times with what we delivered, but also having heard all of their battle stories and seen all their battle scars from when things have not worked out so well. And the soft intro to this is a free email course, which we just recently launched and which you can find from our webpage. We will also send out links after the presentation. So we call this 5 mistakes preventing experimentalists from getting value from simulations, and a subtitle, how you can change that. So that's just a lot of common mistakes we see almost everyone doing when they first try simulation and AI tools in materials R&D. But you could also just ask for a free consultation. Again, this is for commercial R&D labs. So we can take a 1 to 2 hour session where we map out basically what are your R&D workflows today. And then we'll give you a report based on that, on what we suggest as action points to move forward. On the other hand, if you're an academic researcher, we are always open to working in collaborations when it makes sense. Of course, we're a little bit bandwidth limited there as well. So bonus points if it's super interesting or very near to what we already have good capabilities for. And then again, if you're planning something further afield, it's also possible to involve us as subcontractors and software providers in publicly funded grant work. So we are generally not too keen on being project partners, but we can participate by delivering our services. And like, even though we're not a party to the consortium, we're very, let's say, hands-on and helping out to the best of ability. And the best time to reach out for us there is when there is a little bit of time before the deadline, so that we can assess how good of a fit is it with what we bring to the table, and do we have the bandwidth for it, and so on, and also how to scope it in a good way. Then regardless of who you are, you can sign up on compularlab.com for a free demo account. This will let you see some results from the multi-scale, from the parts of the multi-scale simulation workflows that are already part of the app, but you will not be able to run any simulations. But what you will be able to do is to make 3 predictions per day with the Formulation Explorer. So that everyone can do, and feel free to tell all your friends and colleagues that might be interested. And if you want any more information about all of this, you can always contact me at rasmus@compulartech.com. Or you could also go to our web page, especially in the news part of it. And that's where we share white papers and blog posts of whatever is new. And you can also, of course, follow us on LinkedIn. That's also a good place to connect if you would like to hear more. So with that, thank you very much again to EMMC for inviting us. And thank you, all of you who showed up today and stayed until the end. And with that, I'm very happy to take questions from the audience.
So thank you so much for a very interesting presentation. Yeah, we've got your details. We'll also share that recording, and please, everyone, get in touch with Rasmus and Compular for collaborations, as he pointed out. So thank you so much.
Thank you very much.